So suppose that you have 1,000 containers that are supposed to be loaded onto a truck. Their weights are independent and identically distributed random variables with mean 5 pounds each and standard deviation 1/10 of a pound. What's the chance that their combined weight will exceed the max weight for the truck? This truck has a hauling capacity of, say, 5,003 pounds, something like that. Okay, so that is what we want to know is what's the chance that the sum of these, maybe we'll call them W's, I goes from 1 to 1,000, exceeds 5,003 pounds. Well, so what I can do is I can standardize each side of this thing here and say that this will be the chance that that the sum goes from 1 to 1,000 minus, now let's see, what's the mean of this sum? It's going to be n, the sample size, times mu, which is 5, right? And then divide by sigma times the square root of the sample size, 0.1 times the square root of 1,000. Okay, so that's the chance that that guy is greater than 5,003 minus, maybe that'll look better, like that, minus 5,000, right, over 0.1 times root 1,000. Okay, but now all of this stuff, all of this is behaving like a standard normal, right? So this is really this is approximately by the central limit theorem. By the central limit theorem, all this is approximately the chance that a standard normal exceeds 3 over 0.1 root 1,000. Okay, so I can put that into my calculator. I get normal CDF of 3 over 0.1 root 1,000 up to, say, 10 to the 99th, and then it's a standard normal, so I use mean 0, standard deviation 1. So normal CDF, 3 over 0.1 over root 1,000, then up to infinity, or 10 to the 99th, I guess. 0, 1. 0.17139 approximately. 0.17139. There's a 17% chance that you go over capacity there. Well, so here's a question then. How many containers do you have to remove to get that probability to fall down below 1%? How many containers must you remove from the batch of 1,000 to diminish this chance to less than 1%? Well, all right, let's try doing this calculation with 999. In fact, I don't really want to go through all of this stuff again. So, you know what? The chance that that this sum of these I goes from 1 to n exceeds 5,003. I think if I think about it a little bit differently, can't I just say that this is normal CDF? Let's just start from 5,003. 5,003. Go all the way up to 10 to the 99th. And then, let's see, but what is it on the average? It should be n times 1,000. That's my new mean, right? N times 1,000. And then the standard deviation is going to be sigma times root n, right? See, right now, I'm thinking about this interpretation of the central limit theorem. How, let's see, I guess, sort of like this. The same way as before, except that, just how is this sum behaving? So sort of like this, right? I could just, I could get rid of that. This sum behaves approximately like a normal with mean mu times n and sigma times root n. Okay? So, I don't know. Now I can, try putting it in my calculator that way. Normal CDF 5003 up to 10 to the 99th. And then, I don't know, whoops, I made a mistake over here. Did you see that? N times 5, right? Sure you catch that. This is the population mean. This is the population standard deviation. Okay? All right, good. So from 5003 all the way over to the right, and then the mean is, I don't know, let's try 999 times 5, and then comma 0.1 times root 999. Okay? And, oh, hey, look at that. We're already under 1%. That's 0.005 something. Okay, good. So this is 0.005685 something, which is certainly less than 1%. So just remove one, just one. Okay, you just have to take one off. What if you wanted to get that probability down below, a tenth of a percent? Well, then you just do the same calculation again. Just change n. You want to know how many can you put on there? I'm just going to change n. Okay, so there we go. 1.9 something times 10 to the negative fifth. So I guess that would do it too. So you just take 2 off, and you diminish the chance to within 1%, a tenth of a percent. Let's do another example. The central limit theorem. So a machine is to be calibrated so that the average amount of soda dispensed is 12 ounces. Now the standard deviation is, let's say, is known to be 1/4 of an ounce per squirt. If you sample 50 times, you put your cup under the dispenser 50 times and see how much comes out. Let's say you get a sample mean of 11.91 ounces. Is this unusual? Well, certainly you can see that the sample mean is less than your target average. But the real question here is that statistically significant? Now, is a tenth of an ounce really practically significant here? Well, I don't know. Who really cares about a tenth of an ounce? But we are talking about the sample mean for 50 trials. It could be statistically significant. Let's one way we can measure how strange this is or how unusual it is by using the central limit theorem. That is, let's calculate the chance that a random sample mean, would be that we would observe this at less or equal to 11.91 ounces, assuming that this is the actual standard deviation and that this is the actual mean, assuming that the machine is really and truly calibrated correctly. Okay, so then this is well, I guess I could just gosh, could I just do it like this? Do I need to write anything else? Could I just say it's normal CDF? I'm going to go from negative 10 to the 99th all the way up to 11.91, right? Because I'm thinking about, right? If it's really calibrated correctly, then that's where the mean ought to be. The sample, the standard deviation for this, and this is what I'm drawing here, is this is the behavior of the sample mean for 50 trials, then this mark should be 12 ounces plus a quarter over root n, right? Okay, so the standard deviation for this sort of behavior curve is a quarter over root 50. Okay, all right. So whereas 11 point whatever is down here somewhere, I want to know. I'm trying to calculate the area to the left of that mark. So the mean there is 12, and standard deviation is a quarter over root 50. Okay, so I'll do that with my calculator. Get normal CDF, negative 10 to the 99th, 11.91, 12, and then I get a quarter over root 50. Oops. Right. I get 0.00545 approximately. Okay. That is pretty small. Okay. That's like 0.5%. So what this tells me is, so like what I observed was like way down here somewhere. And so this is, in statistics, we call this a p-value, 0.00545. In probability, we call it a p-value. So if in fact the machine is really, calibrated correctly, and the mean is at 12 ounces, and this is the standard deviation, then we've observed something that's pretty small. Okay. Notice again that there's no information in here about the actual distribution of the squirts of the soda, right? What we're applying here is the central limit theorem. We're assuming that 50 is a pretty large sample, and that so that we can actually, I guess this ought to be approximately, right?